Welcome back. We're going to be looking at exceptions today. And this is a fundamental mechanism in C++ for dealing with all sorts of nasty conditions. So let's get started. So first, what are exceptions? They are a basic control flow mechanism that allows us to change the control flow, modify it, in order to deal with, well, as you guessed, the name indicates, exceptional circumstance. And these are typically errors. For example, you expect to have a working network connection and to read from it, but the network went down. When you try, well, you get back an error. What do you do in that case? This is a C++ specific concept. It doesn't exist in C, so pay attention to that. That's new. Great. So how do we live if we don't have exceptions? That's the first question we should be asking, right? What could we do in a language like C? Well, the idea is if one has an error, it's important that every routine that can encounter an error must, at all costs, return a status to indicate whether it completed its job successfully or if it encountered an error. And typically, if it encountered an error, it would like to use that status to report to you the nature of the error, right? Was that a network failure? Was that a communication failure? Was that a division by zero? What happened? Something went wrong. You want to know what went wrong so that you can report it maybe with a nice message to the user interface for the user of your program to actually deal with that situation. So that's the important thing. You need to report the status. And note that it's not just the function that raises the error that needs to worry about this. It's anything that calls it. Right? So if you have function A that calls function B, that calls function C, that calls function D, and D makes the error, D is going to report it, but then the guys in between, B and C, must, if they are unable to deal with the error themselves, they must take this error and say, oh God, something went wrong. I myself cannot terminate because whoever I was relying on could not terminate either. So I've got to pass the hot potato back up the chain. And therefore B, or C in this case, C is not going to do anything and pass it back to B. B is going to look at this and say, oh my God, something went wrong with my callee. I can't deal with it personally, so the only thing I can do is pass it back to whoever called him, which is function A. Hopefully function A planned for this, and function A says, oh, something happened, the network went down. I got to pop up a dialog box informing the user, and he knows that the network went down because the status says, the status that we are reporting that came ultimately from D and flew back the chain to the initial caller A, that status tells us what happened, so A can produce a suitable error message to alert the user and deal with the failure. That's not easy, right? So it creates a whole sorts of problem, right? Because if you want to return a status, how do you do that? Well, the typical way is to say, oh, I'm going to use the return value of the function. My function is not going to return void, it's going to return a status. Well, that's great until you, of course, write a function that was already returning a value. Now it needs to return a value and a status. How do you do that? Okay, you have to think. You can package the status and the return value in a structure. And now each time you return, you manufacture a structure containing both the status and the error value and the normal value. If you have an error, the status will say so. If you have no error, then you pick the other field of the structure that gives you the return of the function. So all your code, when he calls a function, gets back a structure, needs to unpack it, look at the status, and then decide what to do, to carry on or not. So it's complicated, it's invasive, it's ugly. Or you can decide, okay, no, I'm going to return my status as a normal return value, but then my real return value, I will make it an argument. And maybe I'll use pass by reference to turn that argument into a read-write argument, and the function can actually write to this. Yeah, well, that means that you have to rewrite your functions as well to accommodate that style. So that's not any better, right? Either solutions is invasive and pollutes your code with consideration that are error management and have nothing to do with the initial logic of your code. And that makes programming much more ugly. The code is difficult to follow as a result. So we don't want to do that. So in summary, that's completely a silly approach. It's extremely heavy because every function that's along the potato chain has to do the hot potato passing to their caller. So it's very heavy, it's invasive, it's tedious. Well, you guessed it, that's not the way to go. And we want to have support in the language to deal with this much more elegantly, and that's what exceptions are for. Exceptions is an elegant mechanism for dealing with that little problem of ours. So C++ offers two mechanisms to deal with that. The first one is a mechanism to report error, and the second one is a mechanism to handle exceptions when they're being raised, right? So the first one, report an error through an exception. The second, handle the exception and do something with it. So what could be exceptions? Well, they can be anything you want. It's a value. And in C++, a value has a very broad meaning. It could be any scalar type, an integer, a float, a character. That's perfectly okay. But it could be also an object. An object, after all, in C++ is a value, which means we've encountered some of those already, things like string. It could be a string. A string is an object. It's completely okay. It could be a pointer. It's completely fine. It could be a reference. That's cool too. Actually, it can be any object. You have no restriction. You, as the designer, have to make a meaningful choice. Now, of course, if you have used Java, you know the typical approach over there. In Java, one makes a class hierarchy of errors. So you have a bunch of objects, and they're within a class hierarchy. And when you're reporting an error, you are throwing objects. That's perfectly fine here too. You can do that, but you're not restricted to this. You can throw strings, and this is where we're going to be starting. We'll be starting with just scalar types since we still haven't touched classes quite yet. We have some way to go before we get there. So now let's stick to something very simple. Let's look at just throwing strings or integers, and that will be sufficient to illustrate most of the concept. But our first stop, of course, is to look at the two fundamental primitives, the one to raise an exception, the one to catch an exception. And we'll look at these two just now. So raising is quite simple. There is nothing to it. It's a statement. It's not an expression. And it has one argument, which is an expression. And this expression will be evaluated, and the value it produces is what will be thrown. Now, by throwing, it means that it's a hot potato. Rather than passing it down to your caller, you're like throwing it up in the air, and then it's going to float, and it's going to land at whatever place where you're ready to catch it. You're throwing a ball, and there is somebody who's going to catch it. It may not be your caller or your caller's caller. It may be 10 functions up the call stack where you have somebody capable of catching that ball. That's how it's going to work. Throwing is just saying, like, I can't go on, I can't deal with this. Here's the hot potato, and the expression evaluates to the hot potato itself, and that can carry all sorts of information. Since it's an object in general, it could have just a message saying what went wrong, or it could be a completely structured thing with an object with lots of attributes that contains gazillions of details about what went wrong. So, your call, right? But for now, we'll deal with just integers and strings. So semantics, normal control flow is altered. You don't go on. When you throw, you stop dead in your track and you exit. The flow is transferred to the place where we will catch this, which could be in your function, in your caller, in your caller's caller. It doesn't matter, right? If there is no catch site in this function, we just return that the ball is passed up the chain. And if there is no catch site there, the ball keeps flowing up automatically with no further effort. So all of this logic in the caller to actually say, oh, did we have a problem? None of this, it's gone. You only deal with it at the places where you're ready to deal with it. Essentially, you keep going back up looking for a catch site. That's what's going on. Now, if you reach the main function and nobody caught the ball, then the operating system will say, like, what are you doing? You raised an error and you were not ready to deal with it. Well, I'm ready as the operating system to deal with this error, and my response will be plain and simple. I will terminate you, the program. You didn't deal with the error. That's a mistake of yours. Now, I have no other recourse than terminating you. So DOS will always deal with an exception, reporting a message to the effect that the exception was not caught, and it will terminate you. So that's a fairly radical way of doing things. but it's kind of neat. One more concept is that you recall that in C++ we can have objects on the stack. When we throw an exception, we're not terminating the execution of the function. And if you remember, an object on the stack would get reclaimed automatically when you leave the function. That is, if you exit the function normally, that memory is reclaimed, which means that the object that was born when you entered the function, at the time you leave the function, the object dies, right? Objects have a lifetime. They get born, they do things, then they die. Dying is calling a destructor. In Java is the finalize method. In the C++ we have the same thing, we'll cover that. The important thing to remember in the context of exception is that when an object dies, or rather, when we throw an exception, we're leaving the function, and therefore the object needs to be deallocated, so the objects that are on the stack will automatically die. It's part of their normal life cycle. Whether you leave the function through the normal control flow path or through an exception flow path, the object is dying. And its destructor will be called automatically on your behalf. That's something that's important to remember, because there is a little bit of a cost associated, and it's particularly true if your object is not completely initialized. And we will revisit that when we cover object constructors, and we will see the safe way to handle initialization when those initialization can fail, because that's possible as well. It's very important to do this properly and use exceptions in the right way. There are some caveats in that case. So keep that in the back of your mind. We will revisit exceptions to amend and precise this a little further as to what is happening when we're throwing and we have constructors and destructors. But the rule of thumb is when you leave a function, whether through the normal path or the exception path, any automatic object is deallocated, and therefore its destructor is going to be called. Great. So what does the syntax look like on the place where you catch? We've seen the throw already. Just throw an expression, and it's a statement. At the catch site, this is what it looks like. You start by saying, I want to try to do block 0. So try is indicating, hey, I want to do something, and that something is susceptible of throwing a hot potato. If it does, I will not come out of block 0 the normal way. I'll have the hot potato coming in the sky towards me, and I want to be able to deal with it. So therefore, I'm going to have what's called catch block. And you can have a bunch of them in a specific order. It's like the switch statement. So here I'm going to have catch with a declaration and a block, catch with a second declaration and a second block, and I could have a third and a fourth. What's going to happen is that when the potato is thrown, the catch clause are going to be examined. And the first catch clause that matches the nature of the potato thrown at you will be handling the ball, will be handling the hot potato. Now, you're saying, like, well, what makes a catch clause adept at catching a specific ball? Well, it depends on the shape of the ball, right? If it's a soccer ball, a basketball, or a volleyball, you catch it differently. Here, the analogy is the type. If the hot potato is an integer, then it's only a catch that's ready to catch integer that should catch it. A catch block that's able to catch strings shouldn't meddle with catching an integer. Same, in a similar fashion, if what you throw is a vector or an object or anything more complex, something that can catch an integer or a string is not apt at catching this kind of animal, and it would have to be skipped. And we would work through the list of catch block until we find a catch block that is capable of catching the hot potato hurtling towards you. That's the main reason why we have several catch blocks. They will be tried in sequence, and the first one that's capable will handle the error. The ones after that won't get a chance. Now you're probably thinking, okay, if I'm checking my catch block in order from first to last for the ability to handle the potato that's thrown, what if none of them can handle it? Well, then you guessed it, right? If none of the catch in this place can handle it, the hot potato is sent back up. Further up, because further up there might be another try block that has catch clauses capable of handling that kind of hot potato. So imagine that here we just have a catch on int and a catch on string, and what I throw is a space station. It's an object, right? I throw a space station. It's coming here, it's caught, and then we examine the catch blocks and we say, oh, if it's an int, let's do block 1. Well, it's a space station, it's not an int, I can't do anything with that. Then therefore the first catch block doesn't do anything. If it's a string, let's do that. Well, the second one says, well, I mean, it's a space station. I can only handle strings, so I can't do anything about it. And I have no other option. So automatically the space station gets back thrown up, and that's the guy up the chain who has another try block, hopefully that's catching a space station that should handle this. If nobody ever catches it, we're back to square zero, and it's the operating system that will say, nobody caught this, it's gotta go, I have to terminate you, you should have handled that specific error. So that's all there is to it. That's how this instruction works. We're going, of course, to look at an example. So here is the description of the semantics of this instruction, right? So we try to run the block. If an exception is raised within that block, then the catch clauses 1 through k are going to be tried in sequence. That's important to see which one gets to execute the block to handle the error. And notice that inside the block you will have the error in your hands because you caught it. So you can look at it, you can print it, you can do whatever you want. And if nobody catches it, it gets rethrown automatically for somebody else to try and handle it. So now, of course, comes the time to give this a shot. And we're going to look at a very simple program. It's not doing anything interesting, but it should be enough to illustrate the principles behind this. And let's do that. So what I do is write a simple program that basically computes a factorial function, and somehow there is an exception being thrown in a case, right? So I've prepared this so that we don't spend too much time so that we don't waste too much time playing with this. And the program is called Silly. Here it is. So let's look at this in sequence. The first thing I want to show you is the main function. So the main function has a try block, which means, okay, I want to execute something that's susceptible. It has the potential of raising an exception. So my try block here is basically saying this block is susceptible of raising an error. This block, well, it's normal C++. So it calls a function factorial, passing it the value 20 and getting back an integer. And once it gets back the integer, it uses the standard output to print a message, the integer, and a carriage return line feed, and then it returns 0 as usual. But of course, we are good citizens, and in the main function, we want to be ready to catch an error that was thrown, and we say, oh, if the hot potato happens to be a string, let's name it S, and once we have that, we will execute this block to deal with it. And the block basically says, uh-oh, something went wrong, and it will print S, the string, the message that was raised at the time something really ugly happened. And of course, I will return 1 because I'm a good citizen and I'm on a Unix OS, and I want to report to the operating system that this program didn't terminate correctly, so it shouldn't return 0. So I'm returning a status code of 1, and how to use that is a different topic. It has nothing to do with C++. All we care about is really this try-catch construction. So here, a try, a single catch instruction, and the ability to deal with errors that are raised during the execution of this code. So let's go back up and look now, of course, at fact, right? That's the important bit. So I'm working my way back up. I'm at the top of the file, and here's my fact function. Well, it's factorial, it's recursive. What do you expect? Fact is fairly straightforward. If n, the argument is 0, we return 1. Yes, of course, factorial of 0 is 1, right? Just in case you have a memory lapse. This is what we're dealing with. And n factorial is none other than n times n minus 1 factorial. And this is what we do when n is positive. Okay? So that's the usual definition. So if n is 0, I return 1. Otherwise, I make the recursive call on n minus 1. I compute that bit. And once I have it, well, normally I would just return RC times n, which is the product of the result times n. That's my factorial. But what I've done here is that I've added a statement. And I've said, if RC happens to be negative, and we're going to throw something. What is the logic here? Well, think about it. When you compute a factorial, it's going to be what? If it's factorial of 6, 6 factorial is 5 times 4 times 3 times 2 times 1. And this is it, right? Times 0 factorial. But 0 factorial, we know it's 1. So that's what we have to contend with. So as we do these products, you notice, of course, that 1 times 1 is positive. 1 times 2 is 2, it's positive. 2 times 3 is 6, it's positive. 6 times 4 is 24, it's positive. What are we talking about here, right? Well, it's always a positive number. How could it be negative? Well, it's negative because an integer is 32-bit in size. And what can happen is that as we do this product from the bottom up, we may reach a point where we have a number, let's imagine 2 billion and a change. And then we multiply it by that's RC, that's the value of RC, 2 billion and change. And then we multiply it by another integer, which is, I don't know, like something like 10, 15. Then what's going to happen? Well, we'll have an overflow. Why? Because the largest representable unsigned integer is 4 billion. And if we have 2 billion times 10, that's 20 billion, it's larger than 4 billion. So we're going to have an overflow, and the number will come back, because here we're dealing with signed integer. Once we have an overflow, the next number would be negative, because it's going to wrap around. So this is a sign that the computation is botched. You shouldn't call factorial on a value that produces a result that doesn't fit in a 32-bit integer. So here I'm saying, if I get an overflow, I don't want to carry on normally. Something terrible happened, and I'm going to throw a string. So I create a string object, and the message of the string is overflow. So I build a string object, and I throw it. So I manufacture my potato, and I throw it up in the air. It gets thrown, and of course, what's going to happen is that you have multiple calls right now. What you need to realize is that your stack looks like this. Here is your stack. You are inside the main function. So here, up here, right, we had the main function. Then if we called factorial of 20, what happened is that we piled up a frame here for fact 20. Fact 20 made a recursive call to fact 19. So we got another frame. Then we pick up another frame for fact 18. So we keep piling up stack frames on the stack. Eventually, we're going to hit way down here, we're going to hit fact 0. And once we do, well, we know what the code does. It returns the value 1, and we start popping these frames. So as we start popping these frames, we compute the multiplication. At some point, the product of those integers is going to overflow. Okay? When it does, the results coming back from the recursive call will be negative. I don't know when it will be. Let's say that we're in frame k. We are at fact k when the overflow happens. So the overflow happens, we throw. Well, what is left is that on the stack, I still have a bunch of frames, right? All these guys are still on the stack, and I have to deal with them, because who's going to handle the hot potato? Is there, in fact, a try-catch construction? No. So none of these guys are ready to deal with the exceptions. So they get popped one after another, and they get removed from the stack, because I'm leaving these functions, not through the normal control flow path, but I'm leaving those functions through the exception path. So all of the frame gets popped. We reach finally main, so we're back here. And in main, we have this construction here. So let's scroll just a little bit to see it. We have this construction in main where we've said, let's try to call factorial 20. And if it doesn't work, we have the ability to catch a string. Well, what was thrown? Well, we have it here, right? What was thrown is clearly a string. So we can catch that. We name the string that was thrown, we name it S, and then we execute this block of code. When we execute this block of code, we say something went wrong, bang, overflow. And then we return 1 to say something terrible just happened. That's all there is to it. That's the normal execution of this program. So let's see it at work and confirm that this is indeed our behavior. So I'm erasing that line. I'm going to take that. But of course, to just illustrate this, I'm not going to start with fact 20. I'm going to start with the more modest factorial 5. Go to my shell, C++ silly.cpp minus O silly minus standard C++ 14, hit return. Now I run silly. Well, factorial of 120, as we've said, it's factorial of 5 is 120, so no surprise. You notice that the execution, it told me result is, so we really went through this specific function. Everything was completely okay. So let's push up to factorial of 10 and see what happens. Okay, well, already factorial of 10, not that much bigger, but the number grew quite a bit, right? So we're getting bigger integers. So clearly you see that as this gets bigger and bigger, at some point we're going to get to an overflow, okay? And I don't know exactly where that is. Well, I do, but so let's try factorial 15 and run it. Okay, well, there we are, right? So this is what? This is 2 billion. Factorial 15 is 2 billion. So what would happen with factorial 16? We would do one more multiplication. 2 billion times anything larger than 2 is going to overflow, right? Because the largest signed integer is 2 billions and change, 2.1. So we know we're going to overflow. So let's get past this so that there are a couple of frames on the stack. So I'll ask for factorial of 20. Go back, compile, run. And this time, of course, we get the message, something went wrong, overflow. So the exception was thrown, the remaining frames were all popped, reach back main, the exception was caught, the message, something went wrong, was printed alongside with the exception. And since the exception was a string, we can print a string without further ado. So that's all there is to it. With this mechanism, we can actually make sure that we can examine our code and verify that everything is completely okay. That's it for today. Next time we're going to be covering range loop, which is the last big control flow instruction of C++. See you next time.